so, to different topics. So first of all, we are going to spend some time on GEMMA, like just to give you an idea of GEMMA, the GEMMA families, and all the models that you can use. And then I will try also to introduce you a framework that allows you essentially to take open models like GEMMA and let's say scale their training, which it could be useful, especially when you have when you start using bigger version of GEMMA, or when you have a lot of data and you want to speed up the process of training of GEMMA. So this is more or less the high-level view of the session of today. But before to start, let me give you an introduction about myself. I'm Nardini. I'm a customer engineer at Google Cloud. So essentially, I spend my time supporting customers of Google Cloud in building AI ML application. And in my free time, so during the weekend, I also like advocating VERTEX AI. So I joined Abby in several conferences. I write blog posts. I did some hackathons and so on. So the agenda of today is essentially this one. So I will start to introduce you why we are talking about GEMMA today, and especially why we are talking about open models now. And this is just one of the. I will just touch one of the reasons why you want to looking at open models, especially if you try to use them for building your application. And then I will give you a brief introduction of GEMMA. And then, because as I said, the idea is that we want to take GEMMA and we want to train the model or tuning the model at scale. I will introduce you Ray, which is a Python open framework that allows you to distribute AI ML workloads. And especially we will talk how we integrated the Ray on VERTEX AI. And then I will try to show you how it's possible to tune GEMMA using Ray on VERTEX AI in step by step. And at the end, we will have some time for take-homes, Q&A, and if you want to share ideas that you might have, that you might build with what I'm going to present today, it would be just great. So let's start to why we are here today talking about GEMMA, and especially why we are talking about GEMMA right now. So this is a chart that you can find in a paper that I link below, that essentially represent the release date of several proprietary and open models with respect of the ELO metrics. And if you look at this, if you look at this chart, essentially is saying two main things. First of all, that the performance between different models at the top. So if we look at the most performing models, is minimal. So essentially, it's like all models, they are converging in terms of performance to some level. But the most important thing is that a small language model, and one of these models is GEMMA, is start outperforming a bigger model that they have been released before. So looking at this chart, it's kind of, it seems like we are reaching a plateau in terms of what we can, the performance that we can get from these models. And more important, there is, right now, there is even more space for open models if you want to build application with to resolve some specific use case or achieve some tasks. So, and why, and the important things to say is that open models has some advantages compared to other models. Here you have some example, but essentially open models allows you to like you can take open models and you can customize them with respect of the task that you are trying to achieve. And you can do that by controlling the entire like tuning or serving pipeline of those models. And of course, if you have this kind of control, you can optimize the way you tune and you serve those models with respect of your the resources that you can access to. Of course, I mean, because you have the control of the entire, like, of both phases, like tuning and serving those models, as I said, you can optimize, and you can also, like,
Sorry for disturbance.
decide.
Excuse me, sir. Your screen is not visible, clearly visible. Could you share your screen?
Ankit, I'm able to share a screen, and please use the
Yeah.
chat so that because this session is getting recorded, use the chat for your issues. It's okay since is supposed to be a showstopper in case the screen was not visible, but it is. But thanks for letting us know, Ankit. But
Okay,
it's actually visible.
okay, ma'am. Okay. I will
Yeah,
switch my check my
cool.
internet connection. So sorry for.
No worries. Thank you. Yeah. For the rest of the session, please use the chat for any question, please. Thank you. Go ahead, Evan.
Okay, no, so as I was saying, so essentially using open models, it allows you to have more control. And so you can like build models that they are more tailored to the to task that you are trying to achieve. And you can do that by creating some kind of efficiency in terms of resources and in terms of, let's say, capabilities that you need in order to serve those models. So with that in mind, now you should like understand why open models are a big thing. And as I said, this is just one one point of view. There are many other reasons why open models are really important today. And so that's why we are here talking about GEMMA. So essentially, GEMMA is a family of open models that are built on top of the same research and technology that has been used to create Gemini models. And as today, like GEMMA is one of the most performing open models that you can find out there. So here you have a a view of the performance of GEMMA with respect to some benchmarks with respect to other models. I don't know why there is some model skipping, but I think it was Mistral model. And GEMMA, as I said, is a family of models. So here you have some of GEMMA models. Starting from the left to the right, you have GEMMA in two versions, instruction tuned and not instruction tuned, and with different dimensions. And then you have a code GEMMA that is a version of GEMMA which is specialized in cone completion and cone generation. And then you also have a recurrent GEMMA, which is a model that has been designed to speed up the process of inference, and at the same time is well suited for a variety of text generation tasks. To these three type of models, three flavors of GEMMA, there is one missing, which is PolyGEMMA, that has been released recently, which also is part of this family. And essentially, you can access to GEMMA with from different using different interface or different frameworks. So, for example, here you have Hugging Face, you have Keras, you have PyTorch, and of course, you can access to GEMMA models from different platforms. So, for example, you can access to GEMMA using VERTEX AI on Google Cloud. And one important thing is that GEMMA has been designed to respect some of the responsible AI principles that we support as a Google. And there is a very well-detailed description of the framework of responsible AI that has been created or has been designed in order to guarantee that GEMMA is a responsible model. So I would suggest you to go and check it out because it's very well designed. It has several components and is I mean, at least it's good if you get familiar with it. But for now, let's assume that you want to use GEMMA. Here you have an example of how to get access to GEMMA 2B, the instruction tune version, using Hugging Face. So if you use Hugging Face in the past, you know that Hugging Face provides a transformer library, which is a library that allows you again to have to get access to a very simple, easy to use interface for transformer models, and GEMMA is supported in this library. And so what you need to do in order to use GEMMA is just initiating the tokenizer associated to GEMMA and the model itself. And then you can provide an input, convert the input using the tokenizer, and then pass the output in the generate method that the library provides in order to, again, generate some text. So this is the basic usage of the model, just using the Hugging Face transformers libraries. Of course, as I said, other libraries, other interfaces are supported, such as Keras and JAX and so on. So this is the basic usage. Now let's imagine that you want to train, you want to fine tune GEMMA with and you collect a significant amount of data, and you want to tune GEMMA not just for one task, but for several tasks. And at the same time, you don't want to use, for example, the small version of GEMMA. You want to use the bigger version of GEMMA. So the fact that you have collected a significant amount of data, and the model that you are trying to tune is bigger than the 2 billion version that I was showing you before, all these two factors implies that you need a significant amount of resources, especially if you want to speed up the process of tuning the model. And also, this amount of resources, it may happen that they cannot be you cannot find this amount of resources just on single VM, so on single instances, but you need more instances in order to distribute the tuning, the data and the tuning of this model. So in order to control this process of, in this case, tuning distribution of GEMMA, or training distribution of GEMMA, you need some kind of orchestration in such a way that you can control how the tuning process is proceeding. It can help you through handling aspects like checkpointing, or it helps you to handle possible failures that can happen during the tuning process. So all these aspects require some kind of frameworks that allow you to distribute the tuning process of these models. So essentially, the question at this point would be, okay, how I can scale up, how I can submit a tuning job of GEMMA on multiple machines in such a way that I control it and I can, let's say, easily running it, or at least, be sure that when I submit the job, or be confident that when I submit the job, I can get it running in the right way, using the right resources and monitoring it. So, and that's when VERTEX AI comes into play. So at this point, probably you are familiar with VERTEX AI. So VERTEX AI is a suite of services that allows you to, let's say, build both predictive and generative AI application. And in VERTEX AI, essentially what you can do is that you can cover the entire model lifecycle of both predictive and generative AI application using all the services that the platform provides. So from the left to the right, you have, for example, services like Model Garden, which allows you to it's essentially a collection of models that you can use in order to solve a particular task, and then you have all the services that allows you to take those models and customize them with respect of your the particular context that where you are trying to apply those that you are trying to use those models, as well as not only adapting them but also serving them in at scale. So with a certain in a way that some performance in terms of serving are in some way guaranteed for you. So this is just an overall picture of what you can do with the platform. And today we are going to focus our attention on one of the services that allows to do that, which is Ray on VERTEX AI, which essentially is going to be the framework that the services that we are going to use in order to tune GEMMA on multiple machines, so in a distributed fashion. So let me give you an introduction of Ray on VERTEX AI. So as I said, if we start on what I was trying to tell you before, so this idea that because the data that you have, or because the dimension of the model that you are working with, you need kind of a set of computational resources that cannot just be provided you on single machine, but they need to be distributed on multiple machine. So imagine that this is the scenario. In the past, each of the steps that essentially characterize the model lifecycle of machine learning model, of AI models, each of the steps they had a different systems that allows you to handle with all the steps. So, for example, if you want to distribute data processing, you have well-known frameworks such as Spark or Apache Beam that allows you to do that. If you want to train an ML model or an AI model in a distributed way, then you have other frameworks that allows to do that. For example, you have TensorFlow, you have Keras, you have PyTorch, and so on for the other steps. So for the hyperparameter search or the model serving. The idea is that having this variety of frameworks to cover the entire model lifecycle introduce some challenges. So you need to create a sort of glue code between those frameworks in such a way that you can able to handle the entire distributed training when you have when you are in this scenario. And so the idea behind Ray is essentially solving this problem. So with Ray, what you get is a unique framework that allows you to cover the entire model lifecycle using one unique interface without that you take care of how put together, how puzzle, let's say, all the libraries in order to handle a distributed process in the ML or AI context. So in other words, Ray is a Python open source, scalable, and distributed computing framework that essentially has been designed to simplify or to make it easy to build and run distributed ML application or AI application. Ray has several components. So first of all, Ray has Ray clusters, which is again, it's the same concept of clusters that you might have. It's a set of machines that they are able to provide you the computational resource that you need in order to run a workload in a distributed fashion. In this case, today we are focusing mainly on ML workloads. Then on top of the cluster, Ray provides you distributed computing library, which essentially allows you to take a function that is written in Python and parallelize it. So this is like sort of, I'm simplifying here, but this is the concept. And then on top of the core library, Ray provides you a set of pre-built library that essentially, the idea is that they cover all the steps of the machine learning lifecycle that I was showing you before, or the AI lifecycle that I was showing you before, in a way that you can distribute it without like in a better way, or just using a unique programming interface. So let's dive into this component. So I just want to spend some words about them. So first of all, again, about the cluster, probably you are familiar with a cluster is essentially, it consists with several nodes, one-end nodes and several worker nodes, which they are there to execute tasks. And then each node has these raylets, which essentially are a component that allows you to manage the worker process. So all the tasks that you submit on the cluster. And of course, in order to manage those tasks, you need a scheduler, which essentially what it does is ensure that you have enough resources to run and handle like the workload that you submit. And then you have an object store, which essentially what it does, it allows you to store all the metadata or all data dependency, let's say so, that your distributed jobs generate in such a way that they can be accessible from different workloads. And of course, the end nodes manage like the it allows you to control the status of the clusters, and so in particular, it allows you to control to verify the status of each nodes and the process that you are running on the node on the cluster itself. So on the node itself. So this is the cluster. Then, as I said, you have a RayCore, which is a Python library for distributed computing, and essentially in RayCore you have three main concepts. The concept of task, which essentially it's represented by Python function that you can decorate using the ray.remote decorator. And by doing this, you convert a Python function in something that can be distributed in a synchronous way on the cluster. The same concept is applied to Python classes. So you have this ray.remote decorator that can be applied for Python classes. And again, it allows you to, you can use this to distribute the classes in such a way that you can maintain the state and you can execute methods as a remote tasks. And then you have objects, which again, as I said, are components that allows you to manage data dependency that your the process that you submit on the cluster requires in order to execute the task itself, so the process itself. On top of the, before to talk about the libraries that are built on top, here is an example, okay? So this is a simple Hello World example of using Ray. So you import the library, then you initiate a Ray session on the with respect to the cluster. Then given a function, which in this case is an Hello World function, you decorate the function using Ray remote. And then what you do, you execute the function asynchronously on the cluster using the .remote method associated to the task that you just created. And then in order to get the result, you use the .get method associated to task. And again, this is how it's how you can use the Ray SDK, the Python Ray, the Ray Python SDK to distribute a simple function on the cluster. As I said, starting from this Ray core library, then you have access to a set of pre-built libraries, which essentially covers all the steps, and they provide a sort of a unified API that allows you to pass data and models and between all the steps of a AI ML lifecycle from data preprocessing to training, tuning, and inference, but again, in a distributed fashion. So this is how it looks like, the library. And one important thing is that the library itself is integrated with all the open ecosystem that you probably use every day with your AI/ML application. Okay, so now you have an idea of what Ray is. But so why, you may wonder why you want to use Ray on Vertex AI? Because compared to what I just told you, I mean, imagine that you have a machine learning code that you want to run in a distributed fashion on an array cluster. Probably you need to like take care of several aspects before you will able to like submit the job itself on that cluster. So you need to provision the infrastructure that you need. So the VMs for the head and the worker nodes. You need to like configure Ray on this cluster or machine. Then you need to take care of setting up the dependencies that you probably want to use on the Ray cluster. So for example, connecting notebook environment or development environment to the cluster. You also need to take care of, for example, setting up the monitoring dashboard that comes with the framework. So all these aspects is something that it might be challenging for you, that you just want to like, you have just a machine learning code or an ML code and you want to distribute it, you want to scale it. So for those reasons, in order to solve these challenges that you may have, we decide to integrate Ray on Vertex AI. So essentially, with Ray on Vertex AI, what you can do is that using the Vertex AI SDK for Python, you can simply create a cluster, and then you submit the job. And the platform itself takes care of setting the cluster in such a way that you can run the job in a distributed fashion. Also, one of the advantages of having Ray on Vertex AI is that as the framework itself, the services itself has been designed to be integrated with other services that we provide on Vertex AI. So for example, you can submit jobs on the Ray cluster directly from the Colab Enterprise. And we also have an integration with the BigQuery to read and write data from BigQuery. So these are just examples of the possible integration that you have. Okay, now that you know what is GEMMA, what is Ray, and why you may want to consider to run Ray on Vertex AI, let's see how you can use Ray on Vertex AI to tune GEMMA. So let's imagine that you want to tune GEMMA in such a way that it generates some summaries using like in a form that it's more close to the form that you expect on your application or maybe in your company. So this is kind of the use case where it's you may want to consider to tune an open model like GEMMA. So in order to tune GEMMA for this use case, so for generating more custom summaries, the steps are this one. So this is more or less the process. So once you set up, like once you have a project on Google Cloud, the first step is creating a Ray cluster. And then once you create the Ray cluster, using always the Vertex AI SDK for Python, you can submit a job which contains all the tuning logics that you already have developed, like prototyped with respect to GEMMA. And then the Ray on the cluster, it will take care of distributing this logic, this code that you build in order to tune GEMMA on the cluster itself. And then because we provide an integration, as I said, one of the advantages is that Ray on Vertex is integrated with Vertex AI. You can then, once the the job, while the job is running, the tuning job is running in a distributed way, you can use a VERTEX AI TensorBoard instance to log how the tuning process, to verify how the tuning process, so to validate the tuning process, looking at the metrics, looking at the shape of the loss function in such a way that you can see if the way you set the distributed training is correct with respect of some metrics that you define. And then at the end, you can also, once you get the model and you're satisfied with the performance, one way, and this is just one way to serve GEMMA, you can decide to use Ray on Vertex to serve GEMMA in batch using the framework itself. So let's dive into all these steps. So the first step, once you get the project on Google Cloud Platform, as I said, you need to create array cluster. And again, this is quite straightforward because as a Google Cloud, we provide an SDK that allows you to declare the resource that you want to associate to the cluster. So in this case, you define some resources related to the head nodes. You define some resources related to the workers that you want to use in order to distribute the tuning job. And as you can imagine, you can also decide to have GPUs attached to each worker. One important thing is that the services support custom images. So if you have some like custom dependencies associated to the tuning job that you're trying to submit, what you can do is that you can start from the base image we provide with Ray on Vertex and create your custom image and use this custom image as a runtime of each end node and each worker nodes inside the cluster. So in this way, in this sense, Ray on Vertex it gives you flexibility to run also the workloads that require some custom dependencies, let's say so. Again, once you define the resources, you can then submit a simple cluster creation job, as you can see here. And again, the services, so Ray on Vertex will take care of provisioning the resources that you define and create the cluster. So once you get the cluster, you can use the method associated provided by the library to get all the specific related to the cluster. And for example, in this case, we can just get the resource name associated to the cluster that I just created. But again, the SDK gives you a lot of information related to the cluster, like, for example, the dashboard address that you can use in order to monitor the cluster and the resource associated. So you can use the SDK to then verify the cluster that has been created. And this is more or less what you get in the UI. Now, in order to submit an application, so in order to distribute tuning job, in this case on Ray on Vertex, so on the cluster that you just created in Ray on Vertex, you can use the VERTEX AI SDK or the Ray Jobs API. It depends on you. I mean, it depends on the way you develop your code. In this case, I'm going to use Ray Jobs API. So as we said, we want to distribute the tuning of GEMMA, right? So, and we want to use, in this case, the Hugging Face transformers library. So as you can imagine, all you need to do is taking the code that you probably already have with GEMMA in the Hugging Face transformers library, and Ray, it requires you to import two additional library. One is the Ray library itself, and the other one is the Ray train library, which contains a module related to transformers that allows you to distribute a workload that you have using the Hugging Face transformer libraries on the cluster, so on the Ray cluster. Then all you need to do is that taking the code that you have and wrapping the code in a training or tuning interface. So this is an example. So as you can see, I have the same code that probably you have seen in with respect of tuning GEMMA using the Eigenvalue transformers library. But what I do, I just wrap the code in a training function, and then I also add callbacks are associated to this process. So in such a way that I can, like, let's say, monitor in some way the tuning job that I'm submitting in a distributed way on the cluster. But more important, what you do is that you convert, you convert the trainer that you define, which is related to the Eigenvalue transformer library, using the prepared trainer of Ray in such a way that from now on the process can be distributed on the cluster. And then what you do is that you define, once you have this training, once you have this training or tuning interface in this case, what you do is that you define the configuration, so the parameters that you want to pass to the distributed workload. You define the scaling configuration. So essentially, you define the resource that you want to associate to this job that you are going to submit to the cluster. So how many workers you want to use, how many, if you want to use a GPU or not. And then optionally, you can also pass run configuration, which allows you, for example, to define checkpointing policies, or in this case, you can leverage the integration of the Ray on Vertex cluster with the Google Cloud bucket to store the checkpoints that you are going to, that the job itself is going to produce while you are running the job. So all this, then you pass in this torch trainer, which again, it's essentially an interface that allows you to get the training function that you defined before and distribute on the cluster itself. And then you submit, like you use the feed method to submit the job. So this is more or less how you define the script in order to transform like a tuning job in a way that it can be distributed. Then once you have this script, then you use, in this case, as I said, we use the Ray job API to initiate the client that is going to submit the job on the cluster. And you define the entry point of the job, passing some parameters. So in this case, the experiment name, the number of workers, if we want to use GPU or not. And then you just submit the job. Once you submit the job, as I said, what you can do is that you can monitor the job using the Ray on Vertex dashboard. And so the Ray dashboard that it comes with the Ray on Vertex cluster that you create. And also what you can do is that you can periodically upload the checkpoints that are generated by the tuning job in a VERTEX AI TensorBoard instance in such a way that you can monitor how the tuning is proceeding. So now that I give you an idea, let's see. I will show you first how to. You can also create the cluster using the UI, and then I will show you how to submit the job, how it looks like in the UI, and then how it looks the integration with TensorBoard. So this is the VERTEX AI UI, and this is how it looks like Ray on Vertex in the UI. So as I said, what you can do is that you can create a cluster by simply giving the cluster a name, decide the version of the image that you want to use, assign the resource of the end nodes, and the resource of the worker nodes in a worker pool. In this case, we create a cluster with 3 machines. And then you just initiate a cluster creation. And once the job associated to the cluster creation ends, you get a cluster up and running with all the specific, and you can get access to this cluster using the integration that the cluster has with Colab Enterprise. So this is how, like, as I said, in the slides, I show you how to do this using the code. Here, I show you how to do this using the UI. Okay, so once you have, as I said, once you have the cluster, you start like working on your tuning code, in this case, the GEMMA code that I was showing you in the slide. And once you get the slide, you can use the Ray Jobs API to submit the job on the Ray cluster. So in this demo, I'm going to show you how to do that. So once you have the code, again, what you do, you initialize the client, and then you define an experiment name. If you want, you can assign an ID to the job. You define the entry point, all the parameters associated to runtime. So if you have some variables that you want to specify, and then you use the Ray Jobs API to submit the job. And you can also like write some helper functions that allow you to monitor. So once you submit the job, this is how this is the Ray dashboard in Ray on VERTEX AI. You can get access to this dashboard from the cluster itself, and thanks to this dashboard, you can monitor the job. So you can see you can simply access to the single job entry, and you can monitor how the tuning process is proceeding. Like for example, if the parameters. So this is how it looks like when you dive into the single job. So it gives you like a nice logs UI that allows you to check how the resources, or sorry, not the resources, but if the process of tuning is going in is proceeding in the right way. But also you can you can monitor the cluster itself and the actors associated to that they may be associated to each jobs in such a way that you can also monitoring the resource consumption with respect to the cluster and the jobs itself. And so this is how it looks like. Once you, again, as I said, once the job successfully run, what you get, thanks to the fact that the services is integrated in Cloud Bucket, all the checkpoints are logged in Google Cloud storage bucket. And what you can do, again, you can use the integration that we provide in order to log the metrics associated to all the tuning process that you just submit in a VERTEX AI TensorBoard UI in such a way that, again, as you can see, you can validate, in this case, the tuning. So you can look at the shape of the loss function or at the metrics that you decide to use during the tuning process and see if the tuning process went, in this case, in the right direction. This is more or less how it looks like in how like a tuning process it will look like on Ray on VERTEX. Okay, so let's assume, as I show you right now, that you submit the job and you get the job successfully is successfully run. So now you have, depending on the checking point policies that you define, you may have different checkpoints. So what you want to do is that getting the best checkpoints and then just use these checkpoints to generate prediction, right? So in this case, again, what you can do, you can leverage the Ray libraries, in particular the tuning one, which allows you to retrieve the best trial and the best checkpoint associated to the trial with respect to a matrix, a target matrix that you have in mind. So in this case, because it's a summarization, we want to get the best checkpoint with respect to the Rougeland sum library, matrix. And once you have this, the rest is quite similar to what you probably do with the eigenphase transformer libraries. So what you do essentially, you take the base model, you take because we use the adapter, the path tuning. You get adapter weights. So what you want to do, you get the base model, you merge the adapter weights to the base model, and you get the new version of GEMMA, and then you can use this new version to generate the summary, which is going to be closer to the one that you expect in terms of content and the shape that you probably wanted to achieve with the tuning process itself. Okay, so this is it. Like, this is a more or less what I want to show you today. So I hope I was clear enough to give you a journey on how you start from an open model and you use Rayon VERTEX AI to scale it. I have just three key messages that I want to pass to conclude. So first of all, scaling machine learning workloads, especially with open model, it can be challenging. Today, I just show a very basic workload. I will show you some resources to show you how things can be challenged while you start working with even more data or bigger models. But the idea is that Ray, the goal of Ray is providing like a sort of simple and unified Python distributed framework that allows you to handle to some of the challenges related to scaling ML workloads. And Ray on VERTEX essentially allows you to get the best of VERTEX AI and execute your machine learning application using Ray in a distributed fashion without just allowing you to focus on coding the application itself rather than focusing on all the infrastructures that probably those applications, when you try to distribute them, needed. So here is a list of resources. I will share the resources with Abby, so you will be able to start exploring them. There are several notebooks. There are blog posts that you can look at, and more is coming. In particular, I'm working on this series, which is called Ray on VERTEX on Medium. So I will try to keep posting some experiments that I do with Ray on VERTEX for running open models and training and serving open models in a distributed way. So feel free to refer to this series, blog post series. And also, again, I hope I was clear enough. But if you have questions and if you want to reach out, here you have my LinkedIn. Feel free to connect. I'm always happy to share ideas and collaborate. But with that, that's it. I don't know, Abby, if we are going to have a Q&A session. But
Thanks, Ivan. That was terrific. And also, we have some questions around the resources. Don't worry, you'll get all the links that Ivan had showed in the end of the session tomorrow, along with the recording. So you'll have all the sessions, all the resources in hand for you to work on some of these topics. And yeah, if you have questions, please use the chat. And also, yeah, right now, since I'll if you're okay, I'll stop recording so you can actually put your hand up and ask questions directly if you have questions related to the session. If it's related to previous sessions, then please use the chat or use the Discord channel if that helps, right? So I'm going to just stop recording for a moment and then we'll resume the Q&A right here.